Hello, my name is David Prentice. This class is through Legacy Ministry College, and it's called Introduction to General Science from a Christian Perspective. It's not a Bible college, it's not a Bible class per se. This is intended for people that are just not very familiar with science, and maybe they've been afraid of science in the past, to give you a little bit of an introduction to it. Now, I do want to let you know that all of the material I'm going to be covering is available online. You can look on the Legacy Ministry College Moodle, which, if you're taking this class, you should know how to get to it. Or the alternative is you can look on my website, which is www.creationorevolution.net. It's creationorevolution.net. There's a link on there that says Creation Science Lessons, US and Overseas. So you click on that, and you will see on the lower half of the page is the material that I'm going to be covering with you. This is chapter 2 of the materials that you'll see on the Legacy Ministry College, and it's a lot of stuff. I wrote a book for this class. So chapter 2 has to do with mathematics and measurement in science. A lot of people are scared of math. Well, sorry, you can't be scared of math. You have to be able to do measurements and use math. I've covered this before in the last lesson, the last chapter. In this world, we have two major families of religions. One is the Eastern religions, such as Hinduism, which is a large percentage of the Earth's population. Hinduism teaches that the physical universe is not really real, that one of the highest gods, perhaps Vishnu, is having a dream, and in the dream, you are part of the dream. You don't really exist independent of the dream of Vishnu. And so you think that you're real, you think the universe is real, but it's all just an illusion. If that's the case, if everything is an illusion, there's no such thing as objective reality. So the universe is not the same for me as it is for you or anybody else. We each have our own perception of reality. So because of that, if it's all just a dream, it's not possible to accurately or measure the universe or know things about it with certainty. So the point is no point. There is no point in studying nature. You can't measure something that's just a dream. Now, on the other hand, Western religions such as Christianity, Islam, Judaism believe that the physical universe really is real, that God has given objective reality to the universe. And so the universe was here before I got here. It'll be here after I'm gone. As a result, it's possible to measure the universe with some degree of accuracy and precision, and we can know things about it with varying degrees of certainty. This leads us to the scientific method. So I hope you realize people say, oh, that creation stuff, that's nothing but religion. Science is religion. Can you prove to a Hindu that the universe really is real? Nope. Can he prove to you the universe really is not real? Nope. These are things that are accepted as religious doctrines. So science owes its existence to the Western religious doctrine that the universe really is real. Come on, my computer gives me a hard time, gentlemen and ladies. Okay, so when we're trying to describe the universe, we can do it in two ways. One way is called qualitative, which is the quality of something. We could say, oh, it's just a very hot day today. How hot? Well, I didn't give you a number. That's qualitative. Or we could say that sound was loud, or we could say that light is bright. Those are all qualitative. But if you're doing science, you need to try to have something that can be measured so that other people can repeat your results. If you want something measurable, you need quantitative. that is, measurements that can be expressed numerically. So, for instance, the results of an experiment might show a temperature change of 15.2 degrees Celsius or a volume difference, a present volume of 83.6 decibels. So, if something doesn't have numbers attached to it, it's very difficult to be confident in the precision. So, where did math come from? Well, nobody one day just said, here's math. We don't know exactly how it developed. The ancient people were very intelligent. We can tell this by some of the construction techniques, by the way the pyramids were oriented, by the way the Roman concrete was, the way the Mayans did things and the Egyptian did things. They were very intelligent. We don't know all of their secrets. We haven't yet learned how to do the work with metal that they have. But we could at least imagine how math might have developed. Suppose that there's the early humans and they see here's a pile of bananas. And so somebody said, oh, look, one banana, two bananas, three bananas, four bananas, five bananas, six bananas. That's counting. But somebody else might have come along and said, well, wait, you just set up a pile of 10 bananas, and here's another pile next to it of 10 bananas. So I could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 20. Or I could just say, well, I have a pile of 10 and another pile of 10. Oh, I'm going to add those. Adding and subtracting are just faster than counting. And then if I've got a pile of 10 bananas and another one and another one and another one and another one. Oh, you know what would be faster than just counting? I'll multiply. Multiplying is just fast adding, and dividing is just fast dividing. There's another thing we can do that somebody made up. We can raise numbers to powers. So if we have, for instance, 2 to the third power, that just means 2 times 2 times 2. The square root of 100, at what number times itself would give you 100? These are just faster methods of multiplying and dividing. So we use these systems of mathematics to try to figure things out. The ancient Greek and Arabic mathematicians developed a system of solving for unknown quantities by using variables. The word algebra is from Arabic, it's aljabra, and the numerals that we use is such as 1, 2, 3, and so forth. Those symbols are Arabic symbols. They're much easier to calculate with than Roman numerals, which would be I, V, D, L, C, M, and so forth. Arabic numerals are just a whole lot easier to work with. So the ancient Egyptians worked out ways to measure things like area using geometry. And geometry is a Greek for earth measure. It was useful to rulers in knowing how much land people had so they could get their maximum amount of tax. For instance, in Genesis chapter 47, verses 19 to 20, the Pharaoh was going to tax the people. So once people had come up, ancient people had come up with methods of determining areas in Egypt and probably other places. Well, there was a guy named Alexander the Great who came along about 330 BC, and he was tutored by a fellow named Aristotle, who was tutored by Socrates, by Plato, who was tutored by Socrates. And Aristotle, when he conquered his whole part of the world, which was Europe, North Africa, West Asia, he spread what he had learned from Aristotle around, and that's the basis of American culture. So Aristotle is very important to us, even though he made a lot of mistakes. His system of logic was passed on through Alexander the Great. So when Alexander the Great conquered Egypt about 330 BC, the Greeks took over the development of geometry. I do want to point out one thing that people will say is an error in the Bible, and it's not an error at all. In Second Chronicles chapter 4, verse 2, there was a description of the basin in the temple that was used to wash out the sacrifices. It said it was 10 cubits across, 30 cubits around. So skeptics will say this is a mistake because that would make the circumference 31.4 cubits, 2 times pi times r and all of that. This is just stupidity on the part of skeptics, stupidity and laziness. You just read 3 more verses in the same chapter to verse 5, and you find the basin was a handbreadth thick, which is about 4 inches all around. So if we use an 18-inch cubit, that would give an inner diameter of about 172 inches. And then if we calculate the outer diameter, it's not going to be 30. It's going to be 31.4. But if you measure on the inside, it's going to be 30.02 cubits. In science, we have something called significant figures, and 30.02 cubits is well within the range of significant figures we would use. So is 30.02 close enough to 30 for you? I would hope so. So this is not a mistake in the Bible. It's just a mistake by lazy people who want to seem like they're so smart. Then later on, after studying things like that, the study of the ratios of sides and triangles led to trigonometry, which is extensively used to calculate distance and angles in physics and astronomy. Then, if you're trying to work with large numbers of numbers, you're going to do statistical analysis. For instance, if you want to make a prediction about who's going to win the next election in the United States, you got millions and millions of voters. You don't go out and talk to every voter and say, what are you going to do? You take what seems to be a representative sample and you apply statistical analysis, and you can get a pretty good idea about the results of large quantities of numbers. And I'm not talking about politics and deception and so forth, but I mean just statistics. We also use certain types of graphs to get a really quick view of a large number of numbers. Those graphs were begun in the 17th century. Rene Descartes, the guy that said, I think, therefore I am, he invented the Cartesian coordinate system with its x, y, and z axes. We also use line graphs, bar graphs, and circle or pie graphs. They were not invented until the late 1700s. The ancient people didn't have the advantage of all of these things. Late 1700s to early 1800s, William Playfair is often given credit for developing the kind of graphs that we do. So these are some examples of the kinds of graphs that we do. Cartesian coordinate system has an x, a y, and a z axis that are mutually perpendicular, and we use those to plot the positions of things in 3 dimensions. Then if you have something where the data is connected, one gradually changes into another one, you could do a line graph. What was the temperature at varying times of the day? It's a continuous. But then if you have some data that's not continuous, for instance, the distance of one star to another star to another star to another star, we would use a bar graph, which is really a form of line graph. And then if we're dealing with percent, with parts of a whole, we would probably use a circle chart, a pie graph. Then there were further developments. Newton was trying to figure out some things about motion of the planets, and he realized the mathematics available was not sufficient to analyze the motion. So he invented differential calculus. This breaks down a complex shape, the orbits of the planets, into an infinite number of infinitely small pieces. Now, working on the other direction, a guy named Leibniz, he's usually credited with integral calculus, which puts together an infinite number of infinitely small pieces into a complex shape. So we think we're pretty smart, right? This was in the 1700s or so. Well, Archimedes, ancient Greek guy, he may have invented both versions of calculus over 2,300 years earlier than these guys, differential and integral calculus. Somebody a few decades back found an ancient papyrus. And papyrus was a very durable material to write on, but the ink would gradually fade away. So people would use the papyrus and scrape off the ink and use it again to write the next thing. Somebody found a papyrus that had not only some religious things on it, but they said, wait, there's indentations in there. And they scraped out the ink and found out that you could analyze this using infrared and things like that. And oh, look at that. Calculus is written there, both differential and integral. And who was the guy that wrote the original thing that we've scraped away everything? That was Archimedes. Archimedes has to have been one of the most brilliant people of all times, if not the most brilliant. Besides inventing both versions of calculus over 2,300 years before these other guys, Archimedes invented the screw. What? The screw? Isn't that obvious? It wasn't obvious to anybody before. Archimedes invented the screw. He invented the lever. He invented the pulley. He invented block and tackle. He invented something commonly called the death ray, where he was in the city of Syracuse, Greece, and it was right on the ocean, right on the sea, and enemy ships would sail right up to the walls to try to attack. So Archimedes realized he could make parabolic mirrors and focus the sunlight onto these ships. It wouldn't be hot enough to instantly make them burst into flames, but it'd be so hot that the sailors would say, my mama did not raise no fool. I'm not going to stay here with this. So it's commonly called the death ray. He also invented a giant claw that was under the water. So if the enemy ship got close to the wall, the claw would come up, crunch, and crush the ship and sink it. He invented a steam powered cannon. He invented catapults. He invented an odometer to keep track of distance. He invented a very complicated astronomical clock, which we're still not sure of the workings of. He also was instrumental in developing many formulas of geometry. He also discovered the principle of buoyancy that we use to design ships. It's called Archimedes' principle. The story supposedly is true that King Hiero of his city, Syracuse, wanted to have a new crown made. He said, I'm so great, so I want a better crown than what I have. So he called in a goldsmith and said, make me a better crown with this block of gold. So the guy said, okay, yes, Your Majesty. And sometime later, he brought back another crown and it weighed the same as the original block of gold, but the king was a little suspicious and he said, I wonder if this guy melted down the gold and kept some for himself and put in a cheaper metal in there. So he called Archimedes, who was his science advisor, kind of like Spock on Star Trek, and said, I want you to figure out for me, did this guy rip me off? Did he melt down some of the gold and keep it for himself and put a cheaper metal in there? So Archimedes was trying to decide how to approach this problem. And supposedly, true story, a few days or weeks later, he went to take a bath. The bathtub was filled all the way up. He got in and the water sloshed over the side. And he said, that's it, Eureka, which is Greek for I found it. So he went running down the street, didn't bother to put any clothes on, but the king wasn't going to cut his head off. So he went running down the street to the palace and said, let's take another block of gold, just like the one that you gave this guy, put it underwater and see how much it displaces, and then put the crown underwater and see how much it displaces. The crown displaced a little more water, which meant that the guy had put a cheaper metal with a different density. So his head came off. There are also a number of problems that we use imaginary numbers for. If you're trying to solve an equation to the second power, you can rearrange it. You can set it to some number times x squared plus some different number times x plus a constant equals c. And then mathematicians rearranged that and found out here's how we can find the exact value of x. Plug it into that formula. using the coefficients from up above, the A, the B, the C. Okay. X is negative B plus or minus the square root of B squared minus 4AC over 2A. Well, that's great. That'll find you the answer if it exists. It may also show you that it doesn't exist. But the formula doesn't work for anything higher than the second power. Something to the third power, the cube, and so forth. Well, it doesn't work. So mathematicians found out that if they tried to determine a general formula for the third power or higher, the formula had to involve the square root of negative numbers. Well, such things don't exist. There are no real numbers that are the square root of a negative number. The square root is what times itself gives you the other thing. So the square root of 100 is 10 or negative 10, because either one times itself gives you 100. But what's the square root of a negative number? There is no such thing. Nevertheless, in order to describe the behavior of physical systems, there had to be imaginary numbers. So imaginary numbers were invented to describe real things. For instance, electrons, waves, similar phenomena in physics and quantum chemistry require imaginary numbers. Schrodinger's wave equation uses imaginary numbers to show that the behavior of matter at the subatomic level can best be described in terms of waves, but you need imaginary numbers for that. Okay, so that's the numbers. Now, how are we going to use the numbers? In order for everyone to get the same results in commerce and science, there need to be some kind of standards of measurements. Well, suppose it's hundreds of years ago and you need some rope to tie up your horse. So you go into the local village to the rope seller and say, I need some rope for my horse. He says, how much? I don't know, one horse worth. If you have a small horse, you buy that much. Somebody else has a bigger horse. They go to the rope seller and say, I need some rope. How much? One horse worth. Yeah, but they're not getting the same amount as you are. You need some kind of a standard. So one of the guys that came up with a system was King Henry I of England several hundred years ago. And he said, I am not very good with accents, I suppose, but he said, we will use the royal foot as the standard. So he took the length of his own foot and had sticks made, and the length of that was called a foot, sent it throughout the kingdom. And so now everybody's going to use the same foot. And if you took the distance from the tip of the royal nose to the outstretched fingertip, that would be 3 times as much. It's a standard thing within human beings. So that would be the yard. But if you need something smaller, you would take the width of the thumb at the widest part, the knuckle, and that happened to be 1/12 of the foot. It's just standards among human bodies. So that became the inch. So the problem is if we based everything on King Henry's body, it's not going to work well when trading with a different country. Now, England imposed its standard throughout the British Empire, which had colonies all over the world, but gradually England lost its influence and people were not quite so thrilled about using the British system. So beginning around 1790, the French began to develop a measuring system called the metric system, or SI, Système International. And metric means from the Greek word for measure. So these guys were working on developing a measuring system that would not be based upon some king's body parts. Instead, they said, let's use something that's the same for everybody in the world. Well, one of the ancient Greeks, Eratosthenes, had calculated how big around the earth was, and he got it to within 50 miles or so. So the French said, we can do better than those English pigs. So they said, let's take the distance all around the world, and that's too big. But let's take 1/4 of the way from the North Pole to the equator through the greatest city on earth, Paris, of course. And we'll divide that into 10 million equal parts. Oh, yes, it was just about the same length as the English yard, about 3 inches more. So that was a convenient amount to work with. So the Earth was the basis of their system. The meter was 1/10 millionth of the distance from the North Pole to the equator. And then once we've got a unit of length, well, let's make a little box that's 1 centimeter on a side, a cubic centimeter. And at the maximum density of water, which is 4 degrees Celsius, okay, the mass of water inside a 1 cubic centimeter box was defined as a gram. And the kilogram was a mass of 1,000 grams. So notice we had the meter, the kilogram. There are a bunch of prefixes that indicate larger or smaller units. A kilo is times 1,000, centi is divided by 100, deci is divided by 10, and so forth. So the kilogram was the mass of the water in a cubic decimeter of water on a side. Well, yeah, that's kind of a lot of syllables. A cubic decimeter. So somebody came up with the idea, let's use a shorter word for that, the liter. The liter is the same as a cubic decimeter. So when you buy your 2 liter bottle of drink, it's just 2 cubic decimeters. So if we want to accelerate a 1 kilogram object, we get the standard for the kilogram from water. And if we wanted accelerated it by 1 meter per second every second, Newton is regarded as one of the greatest scientists of all time. So the unit of force is called a Newton. If we spread that out over a square meter, 1 Newton over 1 square meter, that's called a Pascal. That's a tiny, tiny, tiny little bit. So for the atmosphere, actually, the for every square meter, it's going to be kilopascals. So if I want to lift an object that has a mass of 1 kilogram lifted by 1 meter, that's called a joule. So how much power do I need in order to do 1 joule of work per second? That's called a watt. A watt? That's right, a watt. These are the metric prefixes. And other than these, you generally will use powers of 10. But if you want to go from the largest one that has a common name, tera, giga, mega, kilo, hecta, deca, and then we have a base unit, which is a meter, a gram, a liter, a second, something like that. And then deci, centi, milli, micro, nano, and pico. And as I used to tell my students, if there's a unit of fright called the boo, 1 trillionth of a boo would be a pico boo. Here's my dumb memory aid for you. There actually was a King Henry who was the one that used his foot as the standard. Okay. So terribly great and mighty King Henry, that's tera, giga, mega, kilo, hecta. And then what happened to him? He died a bad death. Well, bad could be miserable for meter, gross for gram, lousy for liter, and so forth. So he died a bad death, chewing moray morsels noisily. He actually did die of food poisoning after eating a moray eel. So terribly great and mighty King Henry died a bad death, chewing moray morsels noisily. So now you're going to remember all the metric system prefixes, right? Of course. Some more things we need to be able to measure. Temperature. The only country in the world that uses the Fahrenheit temperature scale is the United States. The freezing point of water is lower when things get dissolved in the water. So Fahrenheit, for some reason, decided 0 would not be when water freezes under normal conditions. He said if we dissolve a lot of stuff in it, 0 would be the temperature at which water would freeze, no matter how much stuff he dissolved in it. So that's 0. It's not pure water. It's water with a lot of stuff dissolved in it. Then he was inventing a temperature scale. So he said, I need something for 100. I'll just define the human body as 100 degrees. And if you know anything about it, you'd say, well, no, wait, we're not 100. We're about 98.6. Yeah, but he didn't have a thermometer to compare. So he used that as the reference for the human body. And then later it was refined better. So he used on his scale pure water. Pure water would freeze at 32 degrees. boil at 212 degrees. So there's an amount of heat energy needed to raise the temperature of 1 pound of water by 1 degree. That's a British thermal unit or a BTU. So your air conditioner is measured in BTUs. Well, that's kind of a strange thing. 1 pound of water by 1 degree. Everybody else in the world uses the Celsius scale. This was another one of those Danish physicists, Celsius, and he said, forget this stuff about dissolving things in water. Just give me some pure water. Okay, let's let it cool down until it freezes. We're going to call that zero. Okay, let's boil it. We're going to call that 100. Okay. So Celsius really makes more sense. We're so used to Fahrenheit in the United States, but everybody else in the world uses a Celsius scale, and you can convert back and forth, but it's kind of complicated. So the amount of heat energy needed to raise the temperature, not of 1 pound of water, but one little old gram of water, that's not much. By 1 degree, it's called a calorie. So when you read your food items, your potato chips and so forth, and it says calories, it's actually talking about kilocalories. There's a lot of stored chemical energy inside potato chips and all sorts of things like that. So if you ever want to do an experiment, you can get something like an empty soft drink can and put a certain amount of water inside of it and put a thermometer in it to see what the temperature is. Set your potato chips on fire underneath it or bread or something, burn something, and you'll see how much did the temperature go up. And you could determine the number of calories that were in your potato chip. Scientists also use the Kelvin scale because the rest of the universe doesn't care about water. Kelvin scale is defined as absolute zero being when all molecular motion stops. So the spacing between the temperatures on the Kelvin scale is the same as the spacing on Celsius, although Kelvin starts 273.16 higher. Absolute zero on the Kelvin scale is minus 273.16 degrees on the Celsius scale. If we're trying to work with mathematics, it can get pretty complicated when you have a whole lot of numbers multiplied by themselves. So exponents are shorthand notation for how many times a number has to be multiplied by itself to give a specific answer. For instance, how many times do you have to multiply 10 by itself to get a million? 6 times. So we write that as 10 to the sixth power. Now, here's a strange thing about mathematics. 10 to the zero is not equal to zero. It's equal to one. It's because of the way math operations are done. In fact, anything to the zero power except for one equals one. 10 to the zero is one. 100 to the zero is one. 5 to the zero is one. 0 to the zero, well, that's weird. That's going to be zero. But everything else to the zero power equals one. A negative exponent does not indicate a negative number. Instead, it's just a shorthand way of putting one on top of a number in a fraction. For instance, if I want to say 1 millionth, I can go 1 over 10 to the sixth power, or I could go 10 to the minus 6. It's not a negative number. It's just saying put a 1 on top of it. We also have something called scientific notation used to write very large or very small numbers. Scientific notation uses one digit before a decimal. You may have other digits afterward, and then 10 to some power. For instance, the distance to the sun, 93 million miles, give or take. You could say it's 93 times a million, but if you want to do it in scientific notation, you can only have one digit before a decimal point. So 93 times 10 to the sixth is wrong. We have to reduce the number before the power of 10. So we raise the exponent to compensate. So instead of 93 times 10 to the sixth, it's 9.3 times 10 to the seventh. If you're trying to measure something and you have good equipment, you may get good results. If you have bad equipment, you may get bad results. So there are two factors involved accuracy and precision. And you might think those quantities or those characteristics are the same. They're not. Accuracy is how close my measurement is to the actual value. So if I pick up a stick and I'm using it as a ruler, well, I say I'm going to define this as a meter. Yeah, but maybe it now really is not a meter. So accuracy is how close you are to the actual value. And who tells you the actual value? Somebody with a lot better equipment than yours, some authority somewhere that has $1 million microscope or something. They will tell you the actual value, and then you work from that. Precision is different. If I shoot an arrow at a target and it keeps going in the same place over and over and over again, like Robin Hood, but it's not the center, my measurement, my shooting is still precise. Precise is repetition. So look at the word precise, P-R-E, and repeat is R-E-P. Pre goes with rep. How close the values are when I repeat my measurement, that depends on the quality of my instruments. So if I have a stick that I said, I don't know, I guess it's about a meter long, and I start measuring things with it, I can report my measurement to the nearest meter or so. But then if I have a stick that the manufacturer put markings every 1/10 of a meter, and I trust the manufacturer, then I can report my measurements to the nearest 1/10 of a meter. So it's a lot more precise. But then if I have a stick with markings every 1/100th of a meter, every centimeter, I can report my measurement to the nearest 1/100th of a meter. The more markings your measuring device has, the more decimal places you can and should report in scientific notation. So remember from last time, I talked about how we can know things. Well, there are many things we know through our five senses. I know a bee sting hurts. I know how to ride a bike. Or if I have a good ruler, I can say I know how long this object is, or a good scale, I know how heavy it is. Okay. But then if I want to determine other things that I really can't check for myself, I do have to rely on the manufacturer of the scale or the meter stick or whatever, that they manufacture the thing correctly. So when I say I know the sun is 93 million miles away, that means I read it in a book somewhere and I decided to trust the author of the book. And I don't sing, Jesus loves me, this I know, for my senses tell me so. No, there are a lot of things you can't tell for yourself. You just decide, I will trust some authority. And then there's also a lot of things that we say we know in science, and it's logic. I personally have never taken 2 trillion somethings and 2 trillion more somethings, put them together and counted them to find out, is it really 4 trillion? I just say, no, okay, logically, I'm going to use the system of logic and determine 2 trillion plus 2 trillion equals 4 trillion. So you really need to have all of those three things: personal experience, authority, and logic when you're doing science. So the reason we use the methods, rules, and procedures we do in math and science is because others made them up based on their personal experience or on some reliable authority or on logic. So now we follow their authority, and this helps us to get consistent results. Here are some review questions for you. And these will be on, some of these questions will be on your test. Why does science require measurement? What's the difference between qualitative and quantitative? In earlier centuries, what was often the basis of measurement systems? What object was used as a basis of measuring length in the original metric system as defined by the French? The metric system identifies fractions or multiples of base units, such as the meter, by using watts. The original definition of a gram was a mass of 1 cubic centimeter of watt. Acceleration is a change of watt over time. On the Fahrenheit temperature scale, watt was defined as the temperature at which water would freeze no matter how much stuff you dissolved in it. And on the Celsius scale, 0 is defined as the temperature at which what kind of water would freeze. What's the name of the absolute temperature scale used by chemists? How much is 10 to the 0 power, or anything to the 0 power with the exception of 0? Scientific notation is used to make it easy to write very what or very what numbers. And then, as a little practice, write the number 12 million in scientific notation. So here are the answers. You should learn these, but you can look at it over and over again. Why does science require measurements? To obtain repeatable, reliable results. What's the difference between qualitative and quantitative data? Qualitative describes some property. It's hot, it's bright, it's loud, without numbers. But quantitative has numbers attached. In earlier centuries, what was often the basis of measurement systems? Body parts of kings. I guess it could be queens too. What object was used as a basis for measuring length in the original metric system as devised by the French? The Earth itself. The metric system identifies fractions or multiples of base units, such as the meter, by using what? Prefixes. The original definition of gram was the mass of 1 cubic centimeter of what? Water. And it had to be at a specific temperature. Acceleration is a change of what over time? Change of velocity. It could be speed or it could be direction or both. Either one is an acceleration. On the Fahrenheit temperature scale, 0 was defined as the temperature at which water would freeze no matter what you dissolved in it. It's gonna freeze. On the Celsius scale, 0 is defined as the temperature at which pure water would freeze. So if you want to get pure water, go to the store and buy some distilled water. That's pure water. That's H2O with nothing else in it. The name of the absolute temperature scale as used by chemists is the Kelvin scale. How much is 10 to the 0? Well, anything to the 0 is 1. Scientific notation is used to make it easier to write very large or very small numbers. And an example of that, the number 12 million in scientific notation would be 1.2 times 10 to the 7th. It's 12 times 10 to the 6th, but in scientific notation, you have to change the exponent 10 to the 7th. Hello, my name is David Prentice. This is chapter 4 of my class on Introduction to General Science from a Christian Perspective. This is not actually a Bible class in that it's not going to be teaching you through the Bible. This is just something to let you see that the Bible is compatible with what we think we know about science, and the Bible is actually our final guide for truth. So if you want to know anything about me, which I don't know why you would, my name is David Prentice. I have a master's degree in education, curriculum, and instruction, Master of Arts in Science Teaching, bachelor's in physics. I taught high school science, certified in physics, chemistry, biology, general science, and all branches of mathematics. So I love science and I love anything relating to science. So when I was asked to do this class, of course, I said that would be a great thing to do. So the materials that I'm going to be sharing are available on the Legacy Ministry College Moodle. And you also can find these on my website, creationorevolution.net, in the section that's entitled Creation Science Lessons, U.S. and Abroad. So let's talk about, this is chapter 4. I'm sorry, chapter 3. It has to do with experimentation in science. Why do we do experiments? Well, we want to make sure that the things we think are correct scientifically really are correct. So we rely upon experimentation. Ancient Greeks did not. You know, an awful lot of our culture came from the ancient Greeks because Alexander the Great conquered his whole known part of the world, which was North Africa, West Asia, and Europe. And so he spread the teachings of his teacher, Aristotle. And Aristotle believed that he could reason things out and he didn't have to bother testing things. So he came up with some ideas that were taught as fact in European universities for 2,000 years in some cases. One thing he said was that all the stars are the same distance away because he looked around and it looked like the stars were the same distance away. The problem was he didn't have a telescope. It hadn't been invented, was not invented until thousands of years later. But the first time anyone observed stellar parallax, they said, oh, the stars are not all the same distance away. Here's a little something for you to do. Pick something like a light fixture, hold your arm out at arm's length and get the thumb between your eyes and the light fixture. So close one eye, then the other eye, then the other eye, then the other eye. And it will look like either your thumb is jumping back and forth or the light is jumping back and forth. That phenomenon is called parallax because there's not that much difference between your thumb versus the light fixture. You can see parallax. Well, when uh, Aristotle looked at the stars, he didn't have a good enough telescope. He didn't have a telescope at all. And the stars were so distant that it looked to him like they were all the same distance. But this was falsified the first time stellar parallax was observed by the astronomers Johnson and Henderson. Aristotle also said that the Earth is the center of the solar system. Well, mathematically, this was falsified around the year 1000 by Copernicus, but he couldn't actually do observations because he didn't have a telescope either. But when Galileo came along, he read about a telescope somebody had invented and he made a better one and he found out, oh, look at that. Yeah, the Earth is not the center of the solar system. You can see all of these other bodies moving around too. Aristotle also said that heavier objects always fall faster. This was falsified by Galileo at the Leaning Tower of Pisa. Aristotle said, well, if I drop a lead weight and I drop a feather at the same time, they're going to fall at different rates. Yes, but the problem was he was ignoring air resistance. So Galileo went to the Leaning Tower of Pisa and he chained together two cannonballs and also had a single cannonball, pushed them off at the same time and said in Italian, look out below. And oh, look at that. They both fell at exactly the same rate. If you can ignore air resistance, then heavier objects do not always fall faster. This was actually tried on the moon. There was an experiment done where somebody dropped a hammer and a feather. And since there's no air up there, they fell at the same rate, a hammer and a feather. Aristotle also said that all objects possess an innate tendency to come to their natural position, to come to rest. Well, Newton said, wait, let's reduce the friction. And look at that, it goes farther. Let's reduce the friction some more, it goes farther. Aristotle was overlooking friction. Objects do not possess an innate tendency to come to rest. Objects respond to forces, and forces of friction can change motion. Aristotle also said, unfortunately, in response to an ancient Greek scientist whose name was Democritus, Democritus said, if I take a chunk of gold and cut it in half, it's still gold. Cut it in half, it's still gold. Cut it in half, it's still gold. But Democritus says there has to be some level where if I cut it one more time, it's not gold anymore. Aristotle said, no, that would imply that there's empty spaces in between your idea of atoms. Well, it turns out that Democritus was right, but we didn't have the technology to check it up until the 1800s. So these things were taught as fact in European universities for 2,000 years. When we do science, I hope you would remember back into chapter 1, lesson 1, there are different ways that we say we know things. One of them is that we use our senses: see, hear, feel, smell, taste. And we notice something, and then once we've used our senses, we define a problem. What is it that I want to know? For instance, does music affect how plants grow? Then, if you don't go out and gather information about the subject, you're really dumb. You're probably wasting a lot of time because people have checked a bunch of different ideas. So you go out and read other people's books, see what's been done. You look for knowledge by authority. And authority is not perfect, certainly not. There have been cases where people did fraudulent things, but the more places you could read the results and get similar results, the more confident you can be about the authorities. And then once you've gotten some sense experience and investigated what other people did, you can then apply deductive logic to formulate a hypothesis. I think if I do this, then that will happen. Okay, so just because you came up with logic doesn't necessarily mean you're right. Now you have to experiment. So that's what this lesson is about: experimentation. You devise some sort of an experiment to test your hypothesis. So now, once again, you're trying to get some sense experience: see, hear, feel, smell, taste. You should repeat the test enough times to be confident of your results. You're using your senses, you're using inductive logic, which is where you look for a pattern. And once you're confident, then you publish your results so that your peers, if you're an astronomer, astronomers, if you're physicists, physicists, your peers can test them to either confirm or refute them. You now become the authority. So, should you believe everything anybody tells you, including me? Well, of course, you should believe what I say. No, one of the most important characteristics of any scientist is being a skeptic. A few years ago, there was a so-called pandemic, and people kept saying, follow the science, follow the science. That's the most anti-scientific statement you could possibly make. Most scientific progress occurs as we build on the work of others. But the great leaps forward usually happen because someone, Einstein, Bohr, Schrodinger, they doubted what almost everybody else thought. So they didn't follow the science. There's no such thing as settled science. Anything is open to question. In fact, one time I was in a discussion, a debate with somebody, and he said that evolution is as firmly established as gravity. Well, guess what? I question gravity. There are multiple ideas about gravity. So you have to not be afraid to question anything. So, have you proved anything? No. The only thing that's absolutely proven in science is that nothing is absolutely proven in science. If you're an honest scientist, you would never say you've proved a hypothesis. There could always be something you overlooked. So, what you should do instead is state whether your hypothesis was supported or falsified. If it was supported, you publish a report in a peer-reviewed technical journal. Peer review would mean that if you're a chemist and you're writing about chemistry, you submit it to a technical journal with other chemists. If you're an astronomer, you submit it to a journal, which is the work of astronomers and so forth. So the peers, your peers, are looking to see if you made a mistake or you overlooked something. So if you read nice things with all sorts of pretty pictures like National Geographic, they're not peer reviewed. These are not done by scientists. They're done by photo editors. If your work passes peer review at the technical journal, it will be published. So what happens is you submit something to a technical journal, whatever magazine it is, then other people are assigned to check your work and try to shoot it down. look for holes in your work. If nobody can find anything, if somebody finds something that they object to, they send it back to you and you respond, and they may say, okay, I'm satisfied. Or if nobody can find any objection, then it will go for publication at that technical journal. So from that point on, now that it's published, other professional scientists may then use your work as a reference to guide them in their experiments. That is, you become the authority. So how do you set up an experiment? Well, the purpose is to try to determine cause and effect. So you came up with some sort of a hypothesis. You're trying to decide what factor do you want to test. For instance, I say the amount of water will affect plant growth. That is, if I change the amount of water, it will have an effect on plant growth. Okay. So I deliberately change only that one factor, which is called the independent variable. It's called that because it's independent of everything but you. So you don't say, well, let me change the amount of water, and also let me change the amount of sunlight, and let me change the brand of plant food. No, you change only one thing and see if the dependent variable changes also. You want to know if the dependent variable depends on the independent variable. Now, time is frequently used as an independent variable. We can't change time, but we can choose when to start and stop measuring it. So, for instance, if I want to know the effect of fertilizer on plant growth, I wouldn't change everything. I would change either the amount or the brand of plant growth, but not both, and then observe whether the growth changed. You should also try to keep every other factor except the one you're testing constant. For instance, all the plants should get the same amount of light and water and are all at the same temperature if I'm checking the brand of plant food. Or if I'm checking the amount of water, keep everything else the same. You only vary one thing, everything else is a constant. So you should use as many experimental subjects as you possibly can to make sure the results are not just because of one test subject's unusual reaction. To make sure you're not overlooking something, you should also have a control group for which you deliberately do not change the independent variable. And meanwhile, you're watching to see if the dependent variable changes anyway. So there's a difference between a constant. A constant is some sort of a factor, like the amount of water. A control group is a group that is kept under the original conditions, and you don't change anything on that to see if the dependent variable changes anyway. If so, you might have overlooked something. The purpose of the control group is to help determine if you might have overlooked something. For instance, if all your plants, including the control group, die, there must have been some other factor of which you're unaware. You should then repeat your experiment as many times as necessary to be confident of your results, especially if you only had a small number of experimental subjects. If you have a small number, you should do it a bunch of times. Or if you have a large number, you may be able to get by with only doing a few times. But once you've got a bunch of results, you should then draw conclusions about whether your hypothesis was confirmed or falsified, and you should be as logical as you possibly can. And then you submit your results for peer review. So in science, how do scientific ideas progress? Well, in science, the word theory is not used the same way it is in ordinary conversation, where in ordinary conversation, we often mean just a guess. People will say evolution is only a theory. No, evolution is not a theory. I'll get to that shortly. But if we are trying to describe what happens, we start with a hypothesis. So if you're trying to determine what's the force of gravity on an object, you're going to try to confirm the law of gravity, or the ones that first came up with it tried to describe what happened. You start as a hypothesis. I think this will cause that. So if you're trying to determine what happens, or if you're trying to determine why it happens, either way, you start with a hypothesis that you test by experimentation. So if the hypothesis is supported by repeated experiments, it never fails a test, we eventually may recognize it as a scientific law or a scientific theory. What's the difference between a scientific law and a theory? A law is simply an attempt to describe what happens. A theory is an attempt to explain why it happens. Laws and theories are not the same, not at all. A law is what happens, a theory is why it happens. But you're trying to test either one. So if your law or your theory fails even in a single test, you have to modify it or discard it. So, for instance, to modify something, back in centuries past, we always believed that what goes up must come down. Every time we had ever tried it, it always worked until the invention of rockets. Oops, now we have something that went up and didn't come down. So that's pretty close. It's always worked except for that case. So we would say, well, let's modify it. We would say what goes up must come down unless it's moving with sufficient velocity to overcome the attraction of gravity. But if you look back at the ideas of the ancient Greeks, they believed that everything on Earth was made of four elements: earth, air, fire, and water. And the stars were made of a fifth element called the quintessence. Do we say we just need to tweak that a little bit? No. Things on Earth are made of dozens and dozens of elements. So we would have to say, no, let's just throw that one out. So something that's almost right, we modify. Something that's really wrong, we discard it. So when we talk about a scientific law, we're talking about things like gravity, thermodynamics, planetary motion, and so forth. Laws are a description of what happens derived from observations. If there are any exceptions ever observed, the law must be corrected or possibly even thrown out. Laws accurately predict the behavior of the systems they describe, and they can often be expressed mathematically. I want you to realize a scientific law doesn't make anything happen. It simply describes what happens without trying to explain why. So the law of gravity, I throw something up, it turns around and comes back down. The law of gravity didn't make anything happen. Gravity did, but the law of gravity is just simply a mathematical expression to try to help us to predict what's the force of gravity. It doesn't tell us why gravity exists in the first place. For that, we need a theory. Okay, well, a theory, there's only one law of gravity, the equation you just saw in the previous panel. We use it to predict how strong gravity is. However, why does gravity exist? This is something we need a theory for. Normally, you're going to have more theories than you do laws. So there are several proposed theories, explanations as to why gravity exists. One is that there are particles called gravitons that are moving between objects. Another is that there's something called a gravity wave. Another is that space is distorted by the presence of matter. So if you're going to try to say that you've come up with a scientific theory, well, you have to be able to envision a test that, if fails, shows that you're wrong. You have to admit, okay, if you do this, I'll admit I'm wrong. So a scientific theory at least has the potential to be falsified. Maybe it hasn't been falsified yet, but it has the potential. So the three ideas of gravitons exchanging from one object to another, or gravity waves, or distortion of space, these qualify as theories because scientists are trying to test them. They may never actually get a successful result. We may never observe gravitons and gravity waves and so forth. We believe we have detected gravity waves, but the scientists are at least trying to test them. So therefore, we would say, yeah, these qualify as theories. A scientific theory may never have actually passed a test, but at least there have been attempts to test it. So what about something that you can't really test? Should you just give up and say, no, I'm resigning my professorship at the university or whatever? No. There was a wonderful poem by John Sachs about the blind men of Hindustan. He said that there were a group of blind men in his poem that went out into the jungle and they happened to encounter an elephant. Now, remember, they're blind. So the first one bumps into the elephant's side and says, "Oh, an elephant is very much like a wall." The next one bumps into a leg of the elephant and says, "Oh, an elephant is like a tree." Another one bumps into a tusk and says, "An elephant is like a spear." Another one bumps into the tail and says, "Oh, an elephant is like a rope." Another one bumps into the little tip of the trunk and he says, "An elephant is like a snake." Another one bumps into the ear and says, "An elephant is like a fan." Well, which one was right? None of them were completely right, but all of them were partially right. So if you're a good scientist and there's something you can't observe directly, you would still try to put together the information that's available to you and come up with not a theory, not a law, but a model. A model is something that sort of helps you wrap your mind around something. So when we talk about the theory of gravity, no, I'm sorry, about the theory of evolution. Evolution is not a theory. There are several different models. So, unfortunately, even some scientists use the word theory in the ordinary sense of just a guess. It's a mistake to say that evolution is only a theory. That's a high compliment. Evolution is not a scientific theory at all because there's no way to test or falsify either the idea that all life came from one common ancestor or that humans came from ape-like ancestors. Well, of course, you can't say that creation is a scientific theory either, but evolution is definitely not a theory. No, rather than a theory, there are a number of untestable and contradictory models of evolution, such as neo-Darwinism, slow, steady, gradual change, versus punctuated equilibria, which is where living things jump from one phase to another. Well, likewise, what people call the Big Bang theory and string theory are untestable, unfalsifiable. So that doesn't mean they're wrong, but it means they're not theories. There are multiple models of each one. Big Bang, you have hot Big Bang, cold Big Bang, expansion of space, a bunch of different things. So they're models. Okay, let's talk about what some of the major divisions of science are. Empirical is a word that means confirmed by experimentation. Empirical science is things that has been tested and can be tested anytime you want. There's also some things that we can't test. These things many times are called historical science. So there's no way to do experiments in the past. So there's no way to test the conclusions of the so-called historical sciences. They may be right, they may be wrong, but they're not science in the same sense as empirical sciences. Now, physics, which is my favorite, that's my background, it's the big picture of how the whole universe operates. It deals with forces, motion, energy, and so forth. Classical physics tends to deal with the description and causes of visible phenomena. It includes such things as astronomy, mechanics, which is the study of motion, thermodynamics, which is the study of heat flow and other forms of energy, acoustics, the study of sound, optics, the study of light, the study of electric fields, magnetic fields. These are all part of classical physics. That's empirical science. You can do experiments on those. Now, modern physics at the largest scale deals with relativity, gravitation, time dilation, and so forth. Those are not as easy to confirm by experimentation. In fact, it's questionable whether some of them ever could be confirmed by experimentation. Those are called historical sciences. So at the largest scale, modern physics deals with relativity, gravitation, time dilation, and so forth. At the smallest scale, it deals with the nature and behavior of subatomic objects and the ultimate causes of fields such as gravity, electricity, magnetism. So the next major division of science that most people are going to need to be aware of is chemistry. It's the study of matter, especially the interaction of atoms and molecules. Some of the major divisions of chemistry are organic chemistry, which deals with carbon-based compounds that usually have their source in living things. Organic chemistry would apply to you and your body. Inorganic chemistry focuses on compounds that are not based on carbon. And I should throw in here that there may be some compounds that contain carbon that are not necessary from living things, like carbon dioxide, carbon monoxide. So that's more toward inorganic chemistry. Analytical chemistry has to do with the composition and the atomic structure of compounds. Some of the focus is on quantitative analysis, how much of this, how many moles of that, how many grams of this. Some is on qualitative. Physical chemistry has a strong overlap with physics. It has to do with the effects of energy on matter and chemical reactions. Nuclear chemistry has to do with the nucleus of the atom. Biochemistry has to do with the chemical reactions and processes that go on within living things. But I want you to realize chemistry can only operate within the laws of physics. Physics is the overall composition of the universe. Chemistry is when you get down to matter. And then biology is the study of all the aspects of life. So the branches that deal with repeatable processes going on in the present, that's part of empirical science, testable. Some of the things that are testable would be zoology, dealing with animal life, botany, focusing on plant life, marine biology, sea life, cell biology, microbiology, bacteriology, and so forth. Those have to do with life at the level of the cell. Now, there's also something that's called historical biology, and I would disagree with this, but evolutionary biology is one of the so-called historical sciences. It tries to describe how present processes in living things must have developed in the prehistoric past because of unknown processes. Well, maybe you're right. And just as likely, maybe you're wrong. There's no way to test historical evolutionary biology. So evolutionary biology would include such things as the origin of life, origin of the genetic code, hypothetical ways living things could have gone from zero genetic information at the beginning to their present extremely complex state. There's no way to test the conclusions of evolutionary biology. And just as I said, chemistry can only operate within the confines of physics, while biology can only operate within the confines of physics and chemistry. Some other divisions of science, you have geology, which is the study of the Earth's structure and processes. Physical geology has to do with repeatable processes going on in the present that we can test. Some of the major divisions would be things like petroleum geology, mineral geology. Plate tectonics, yes, we can predict, we can analyze the motion of the continental plates, and the other aspects such as seismology, which is a study of earthquakes, and volcanology. Oceanography and meteorology, having to do with the sea, with the weather, those are closely related to geology. Now, there's also something that's called historical geology. It's an attempt to determine past processes by looking at those occurring in the present. It deals with such topics as the age of the Earth, the processes believed to have produced its present features. Historical geology is based on an unprovable statement. The present is the key to the past. How do you know the present is the key to the past? Well, because my teacher said so. There's no way to test that statement or any of the conclusions drawn from it. Now, if you're a Christian, you should compare historical geology to 2 Peter chapter 3, verses 3 through 6. This was a fisherman, a guy named Peter. Yes, but he was called by Jesus to be one of his apostles, and he wrote several books of the New Testament. So there's a principle used in historical geology called uniformitarianism, that is, present processes at present rates can explain the entire geologic record. This is what Peter warned us about, the idea that the present is the key to the past. Peter warned us, 2 Peter chapter 3, verses 3 through 7. He said, knowing this first, that there shall come in the last days scoffers, walking after their own lusts, and saying, where's the promise of his coming? For since the fathers fell asleep, all things continue as they were from the beginning of the creation. For this they, the scoffers, willingly are ignorant of, that by the word of God the heavens were of old, and the earth standing out of the water and in the water, whereby the world that then was, being overflowed with water, perished. Peter said, look out for this. In the last days, scoffers will say, there has never been a worldwide flood. That's where we get the idea that present is the key to the past. There is no worldwide flood in the present, so there cannot have been one in the past. If there was one, you just threw out the entire time scale. So here are the things that are considered historical sciences. Cosmology studies the processes that produce the universe. There are very few cosmologists that accept the biblical account of creation. Most try to explain the universe as a result of a big bang or steady state universe or something like that. Anything except in the beginning God created. Paleontology is the study of fossils. Some of it consists of comparing the anatomy of extinct animals to living ones. But there are also many, not all, many paleontologists deny the biblical account of creation and the flood, and they're trying to explain how living and extinct things must have evolved. Archaeologists attempt to draw conclusions by examining such things as relics. Their conclusions are almost never testable. You look at other information that's known and is available, and you try to draw some logical conclusions, but you can't test it. And then forensics, which is a singular word, even though it has an S at the end, it's the use of science and technology in an attempt to establish facts in historical or legal matters. So, for instance, crime scene investigators might use physics to determine the height of a shooter by calculating the trajectory of a bullet. They also might use chemistry to determine whether the mud on a person's shoes is likely to have come from a specific site. They might use biology to determine how long a person has been dead by observing the insect larvae in a corpse. So forensics doesn't directly observe what's going on, but it applies strongly to other things that you can test. So let's think about some review questions. Why is peer review important in science? And you can look back through the chapter, or you could cheat and look on ahead in this video. Why is it important to have only one independent variable in an experiment? And then what's the purpose of having a control group in an experiment? What's the purpose of a scientific law? What's the purpose of a scientific theory? Why is it incorrect to say evolution is only a theory? Since we cannot directly test phenomena that are too big, too small, too slow, too fast, past, future, and so forth, what can we do to try to understand these phenomena better? What does empirical mean? What's the difference between empirical science, also called operational science, versus so-called historical science? Give an example of an empirical part of biology. Give an example of something usually considered part of biology that should instead be called historical biology. That is, it's not empirical. What is uniformitarianism? What? That doesn't mean you have to wear a uniform. How does 2 Peter chapter 3, verses 3 through 6 tell us that uniformitarianism is wrong? Think about those. Now let's move on. Why is peer review important in science? To avoid mistakes, to reduce bias, to make sure proper procedures are followed. Why is it important to have only one independent variable in an experiment? You're trying to establish cause and effect, so you only allow one thing to change. You can be confident that the independent variable caused the change in the dependent variable, that is, cause and effect. What's the purpose of having a control group in an experiment? It's to be sure you're not overlooking some unknown factor. What's the purpose of a scientific law? It's to describe what happens. What's the purpose of a scientific theory? To try to explain why it happens. Why is it incorrect to say evolution is only a theory? It's not a theory because it cannot be tested. There are actually multiple models of evolution, but none of them can be tested. Since we can't directly test phenomena that are too big, too small, too slow, too fast, past, future, and so forth, what do we do to try to understand them? We use scientific models. What does empirical mean? Determined by experimentation. What's the difference between empirical or operational science versus historical? Empirical can be tested, historical cannot. Give an example of an empirical part of biology. There are many, but they could include things like how things grow, how they reproduce, how they interact with the environment, many other things like that that are going on in the present and can be tested. So give an example of something usually considered part of biology that should instead be called historical biology. Well, there are many of them, but one of them obviously is evolution. Can we test that? No. How did life begin? Well, we can't test that either. And did humans come from apes? Can't test that either. What is uniformitarianism? It's the idea that the Earth's geologic features form slowly, steadily, and gradually over millions of years. There can never have been a worldwide flood. And how does 2 Peter chapter 3, verses 3 through 6 tell us that's wrong? It says that's what scoffers are going to say, and they will deny that there was ever a worldwide flood. Okay, so this concludes this chapter, and you'll see the continuation in the next one where we get into specifics about various branches of science.